This is part 2 of our video on H1, Appendix H1 and Appendix H2 Solutions. We left off on video 1 with starting problem 31. 31 asks us to sketch the curve with the given polar equation. So we have this equation, 4 sine 3 theta, and I said one way to do this in class was to plot points, but a second way to do this, right, is to draw the graph of the trig function and then transform that graph onto our polar axis. So I'll demonstrate that technique now. 4 sine 3 theta, right? We know that the amplitude is of this, the amplitude is going to be 4 because that's 4 there. This is of the form a sine, and I don't know what variable you used in your pre-calc book, but we could call this alpha theta. And the period of this is going to be 2 pi divided by the absolute value of alpha. So for us, that's 2 pi divided by 3. So we have a sine curve whose amplitude is 4 and whose period is 2 pi divided by 3. So if we draw that, that curve's going to look like this. This is 4. This is -4. And this is 2 pi divided by 3. So this is pi over 3 here, half of the full period. This is pi over 6, and this is 1 pi over 6, 2 pi over 6. This is going to be 3 pi over 6, which of course is 2 pi. Now, our approach here is to take this graph, treat this as r, and this is theta, and transfer that graph onto our polar graph here. Now, we did an example like this in class, but I'll go through this step by step. This is 0, 0 here. That's where theta is 0, or angle is 0. And on the polar axis, remember the polar axis is really just this, but we put the x, y coordinate on top just to help ourselves with our orientation. So our angle is 0, so that means we're on this axis, and the length of our radius is 0, so our initial point is here. Now, pi over 6 is, 30 degrees, that's over here. And when we get to pi over 6, our radius, r is going to be 4. So we're 4 units out. We'll call this 4. Now, what happened is we plotted that point and that point, but we didn't plot any of the points in between. So to plot the points in between, we're just going to walk ourselves through this. We're going to say to ourselves, okay, my angle starts at 0, theta is 0 here, and my angle goes to pi over 6. So I'm going to touch all the angles from 0 to pi over 6. And while we're doing that, our radius is going to grow from 0 to 4. So at each of these angles, I'm not going to draw every angle, but at each of these angles, my radius would be getting bigger and bigger and bigger as I move through the angle. So our graph is going to look something like this. Now, we could put a little 1 next to this in a circle and a 1 up here in a circle to say that part of the graph of the sine curve corresponds to this part of our polar graph. Now, what goes on from pi over 6 to pi over 3? Well, from pi over 6 to pi over 3, our radius starts at pi over 6 at 4, this point here, and it's going to go all the way back to 0, right? This point is 0 pi over 3. Now, pi over 3 is on the 60-degree angle, but we're going to be back here at 0. And as we go back, our radius is going to get shorter and shorter and shorter. So our R values are going to get smaller and smaller and smaller. We're going to move from 4 back to 0 on our radius as our angle moves from pi over 6 to pi over 3. So this would be part 2, and that would correspond to this here, part 2. Now, what else is going to happen? Well, from pi over 3 to, this is really pi over 2, right? Pi over 2, 3 pi over 6, pi over 2. Pi over 2 is here. From pi over 3 to pi over 6, our radius goes from 0 to 4. Remember, we can't have a negative radius. The negative sign, we'll take that into account here in a second. But our radius is going to be 4. This height is 4 down here. It's negative. So we would be obviously at pi over 3, we're at 0. We're back on this dot. But as we move to pi over 2, we're going to be 4 units away, but we're negative 4 units away. Negative 4 means we reflect through the pole. So even though we're at pi over 2, we would reflect, and we would, because our r is negative, we reflect through the pole. Now, what happened to those r values as our angles changed, right? As our angles changed, our values got bigger and bigger and bigger. Each of our r values got bigger and bigger and bigger. Now, while they were negative, they were getting closer and closer to negative 4. Again, the negative just means a reflection. So while we were going from pi over 3 to pi over 2, if we did not have a negative r, if we were not below the x-axis, we would have had a graph that went up like this. But we've reflected through the pole. So while we would have been here, now we're down here, because when we do our reflection through the pole, we have to reflect through x and reflect through y. So this is segment 3, and this is segment 3. Now for the next segment, we were at 4, right? We would be up here, except for the fact that we have a negative. We were here, and we went all the way to 2 pi over 3, which would be on this angle, and we would have moved back to 0. But again, we're reflecting through the pole. And so now we're down here. This is segment 4. Now we haven't completed the graph, and that doesn't look very good, does it? I mean, that's about as symmetric as. So we have 2 sides of our rows right now. We're going to get the third part of our rows by completing this graph up and back down. This is pi over 3, this is 2 pi over 3, this is 3 pi over 3. And at 3 pi over 3, and then of course this is pi over 6, 2 pi, 3 pi over 6, 4 pi over 6, this is 5 pi over 6. So from 2 pi over 3, our r value has switched. We're above the x-axis, so our r value is positive, so we're not going to do a reflection. At 2 pi over 3, which is right here, we're at 0, so we're back at this dot. Now, as we move from 2 pi over 3 to 5 pi over 6, 5 pi over 6 is here. We're at 0 at 2 pi over 3, and our radius grows until we get to 4. And at 5 pi over 6, we're at 5 pi over 6, 4. So that puts us here. So that's the 5th portion of this curve. And now we have one last piece. We're going to go to 5 pi over 6 back to pi. So our angles are going to go through this range here. But as we go through that range, our smallest angle is going to be, our smallest r value is going to be at pi. And so we're going to complete our 3-sided rows, each of these distances being 4. So that's how we do our graphs from polar. We draw the graph of the trig function. We then trace the trig function's r values and theta values onto our polar axis, and we generate our polar graph. All right, so that's problem 31. If you hear some background noise, I apologize. My lab is up here, and she has just completed a very vigorous exercise session, so she's up here. I'm hoping you can't hear her panting away in the background, but if you do, I apologize. On problems, we have also problems 48 and 49. Now, 49 and 50. Those problems ask us to find the slope. So if we look at problem 50, we need the formula for the slope because it says find the slope of the tangent line to the polar curve, and they give us a curve r equals 2 minus sine theta, and they give us an angle. We're supposed to find the slope at theta equals pi over 3. So we want to find the derivative, and we want to plug in pi over 3, and that would tell us the slope of our tangent line. Now, how are we going to find the slope? Well, we have to take the derivative, and the derivative, remember, dy dx, the derivative is going to be dy d theta divided by dx d theta. That's just an adaptation of the chain rule. Now, if you don't remember what dy d theta is, you know y equals r sine theta, so you can just figure it out. You're going to use the product rule, and you're going to get the derivative of r with respect to theta, right? Because this is r times sine theta. So that would be dr d theta times sine theta. We're doing the product rule, plus, and then we're going to get our r, and we're going to take the derivative of sine theta, which is going to give us cosine theta. So our numerator for our formula is dr d theta sine theta plus r cosine theta. And we would find dx d theta, again, if we don't remember this formula, x is equal to r cosine theta. So dx d theta is the derivative of r, that's dr d theta, times cosine against product rule, plus r times the derivative of cosine, which is minus sine theta. So if you don't have this memorized, you can always take just a couple of minutes and write out, by using the product rule twice, the formula for dy dx in terms of polar. Of course, this is minus r sine theta. So to do our tangent, which is what they asked us for in problem 50, they want us to find the equation of the, they don't want the equation part of it, they just want the tangent line. So we're now going to plug in theta equals pi over 3. Now, here we have dr d theta. Here's r, so we're going to have to find that, right? So what is dr d theta? Dr d theta for us is the derivative of this in terms of theta. The derivative of 2, that's a constant, that's 0. The derivative of sine is cosine, so this is going to be minus cosine of theta. Now we're going to want to evaluate that at theta equals pi over 3. And when we do that, we're going to plug in pi over 3. And again, if you can't remember, you can always just draw your triangle. Here's pi over 3. That's 1, 2, square root of 3. The cosine is going to be adjacent over hypotenuse. That's going to be a half. And we have a negative sign, so we're going to get negative 1/2 for dr d theta. So when we come over here to our formula, we can plug that in. That's going to be negative 1/2 times the sine of theta. Theta, remember, is pi over 3. Here's our 30, 60, 90 triangle right here. Sine is root 3 over 2. So we're going to have the square root of 3 over 2 for sine minus r. Well, we don't know what r is when we plug in pi over 3. So we can figure that out over here on our scratch area. R is 2 minus cosine of theta, or r is going to be 2 minus, and then we said cosine of theta was a half, right? Cosine of theta adjacent over hypotenuse, that's a half. So we're going to get 3/2 there. So for r right here, we need r at theta, and r at theta was 3/2. We're going to plug that in there. Times cosine of theta. Cosine of theta is 1/2, so we're going to get a 1/2 right there. Divided by, we have dr d theta. Now we already figured out dr d theta. That's minus 1/2. We need cosine of theta. We just found cosine of theta. We know cosine of theta is right here, i.e. it's right there. Or we can come back to our triangle and get 1/2. And then we have minus. Now we need r, which was 3/2 sine of theta. The sine of theta, right? The sine of theta is root 3 over 2. So if we take a look at what we have here, right, we can do some algebra 2, hopefully in our heads. There's a 1/2 and a 1/2. There's a 1/2 and a 1/2. Here's a 1/2 and a 1/2. Here's a 1/2 and a 1/2. All those are 1/4, right? A half times a half, a half times a half, a half times a half, a half times a half. Those are all 1/4. So we actually can factor out a 1/4 on the top. That would leave me here minus √3. And here I would have minus 3. I can factor out a 1/4 on the bottom. Here I would have a 1 times 1, that would be a -1. Here I would have 3 times √3 with a negative sign from here, minus 3 √3. And so those 4's cancel. And so what do we end up with? We end up with negative √3 minus 3 divided by -1 minus 3 √3. Of course, we can multiply the top and the bottom by -1, and we get √3 minus 3 divided by 1 minus, sorry, we factored out a negative sign, so these are going to be pluses. So everybody would be positive. And we end up with √3 plus 3 divided by 1 plus 3 √3. Now, if they asked us to find the equation of the tangent line, right? They asked us for the equation of the tangent line, which they did not do in the problem, but just in case it comes up, we would have to go back to our point slope formula. And we would have to find our y value and our x value. Now, we would find our y value and our x value using this formula right here. We would know r, right? We found r. Remember, we found r. R is right here. R is 3/2. And we know what theta is. Theta is pi/3. So we could put those into each of these formulas and find y and find x. For example, we would get y equals r, which we said was 3/2 at our point, at our angle, which was pi/3. R is 3/2. We found that earlier in the problem. So that goes r times sine of theta. Sine of theta is √3/2. And we would have 3 √3 divided by 4. That would be our y value, and that would go right there. We know our slope. We found that. It's right here. This is our slope. And we would use a similar formula, except we would use this formula, the formula for x, but a similar idea or a similar approach. And we would plug in r and theta there, and we would get our x value. We'd plug them into our point slope formula. We'd have the equation of our tangent line. All right. The other problems that are in the homework are 53 and 55, and they ask us to determine when the tangent line is horizontal and when the tangent line is vertical. To do those problems, you take your formula for your derivative, the formula we have right here. So you find the formula for your derivative, and horizontal, of course, you want to set dy dx equal to 0, because if the slope is 0, the tangent line is horizontal. Now, this slope is a fraction. Fractions equal 0 when the numerator is 0. So you would, to do the horizontal tangents, you would take just the numerator and set that equal to 0. That's what you would do for horizontal. But for vertical, right, for vertical, we would want to know when is dy over dx undefined. When is that undefined? Well, again, it's a fraction. To determine when it's undefined, you would take the denominator and set that equal to 0. So you would need to set up those equations, those trig equations, and see when each of them are equal to 0. And that's how you solve problems 53 and 55. Now that completes our homework in section H1. So I'll do a couple of problems. We didn't have very many problems from H2. And most of the problems in H2 are very similar. We are only taught 2 formulas. So I'll do 2 problems from there just to get you off and running. And then that will complete our videos for Appendices H1 and H2. Remember in H2, we had two formulas. We had the formula for the area of a region if we're given that in polar coordinates, and then we had the formula for the length of a curve in polar form. And so if we take a look at the homework problems in H1 and H2, let me turn the page here and make sure I'm on the correct page. In the beginning, the first problems were 6 and 7, and then 11, and then 15 and 17. And they all ask for the same thing. They all ask us to find the area shown either in the graph or find the area of the given polar region. So we would then first have to draw the graph. And then once we draw the graph, then we would have to find the area. So I'll just do problem number 11. It's typical of all the problems. And that one involves having to draw the graph. So let's take a look at that. We have R equals 2 cosine 3 theta. Now, this turns out to be a very similar graph to what we looked at before. We just did that as the first problem in this video, question 31. We had 4 cosine 3 theta. And what we said there was that if you remember, we said this was 2 pi over 3. So this was pi over 3. This was pi over 6. 3 pi over 6, 5 pi over 6, and finally, this was 3 pi over 3, or pi. And when we drew the graph of this, right, we got a 3 petal rows. Our first petal went along the axis, or along the angle pi over 6, and it went out like this, and it came back like this. Our next petal was on this axis down here, and it went down here, and it went back to here. And then finally, our third petal went along the angle 5 pi over 6, and it went out here and came back through here. And what they asked us to do in problem 11 is to find the area of this, right? The area of this. Now, in this case, our magnitude was 2, so that length is 2, and that length is 2, and that length is 2. Now, we have a formula, right? We have a formula for the area, and our formula for the area is area equals the integral from A to B, and we have 1/2 f of theta squared d theta, right? That's our formula for finding the area. Or if you don't like it in that version, we also wrote it as the integral from A to B of 1/2 r squared. Oh, sorry, I forgot a parentheses there. R squared d theta, whichever way, sometimes they might write this function as f of theta instead of r, function of theta. So from here, we need to take a look at our picture, and then we need to have a conversation with ourselves. We need to think about symmetry and how symmetry can help us. What am I saying? Although my picture is not very well drawn, right? I mean, it doesn't look very symmetric the way it's drawn right now. We can see by looking at our picture that this region right here, if all we're going to talk about is area, that half of that petal is reproduced 6 times, right? If all we're doing is talking about area, and that's what the question's asking us, we can just find the area of this piece of the petal right here, which would be the integral from 0 to pi over 6. And then we can put in our formula. We would have 1/2. We would have our R value, which is 2 cosine 3 theta squared d theta. We can find that. And then just since it's reproduced due to symmetry, not just once, twice, 3 times, 4 times, 5 times, 6 times, we could just multiply this by 6. Now, when we bring the half out, that would give us 3 times the integral from 0 to pi over 6. And here we would have 4, right? We're going to square this. This is going to be 4. And then cosine squared 3 theta d theta. Now we can put the 4 out in front. And now we have 12 times the integral from 0 to pi over 6 of just cosine squared 3 theta d theta, all right? So this is a integral, a trig integral, even power of cosine that we've done in the past. We learned how to do this in section 5.7, I think. In section 5.7, we're going to use a half angle identity here. So this is going to be 12, integral from 0 to pi over 6. And then we're going to replace cosine squared, of course, with 1 plus the half angle identity for cosine. Now that's going to be cosine. Normally, if this is cosine x, this is cosine 2x. But this time, this is cosine 3x, so we still have to multiply by 2, so we're going to get cosine 6 theta here. Now remember, we have to divide that by a half, because that's our half angle identity, right? Our half angle identity is cosine squared x equals 1 plus cosine 2x. So we multiply whatever angle we find here by 2. Our angle was 3, so multiply that by 2. That's where the 6 came from. And then we got to divide by 2. Now that 2 can come out here and make this a 6. Man, this constant is just flip-flopping everywhere. First it was 6, then it became 3, then it became 12. Now it's back to 6 because this half times this 12, that gives us a 6. Integral from 0 to pi over 6 of the quantity 1 plus cosine 6 theta d theta. Now, when we integrate 1, we're going to get, don't lose your 6, we're going to get integral 1, that's going to be theta. The integral of cosine is sine. Now, we're going to need a u sub, so we're going to need to multiply by 6, which means we have to divide by 6. So we're going to get sine of 6 theta, and then from the u sub, we had to divide by 6. We're going to evaluate that between 0 and pi over 6. So here's our 6. We're going to plug in pi over 6, so that theta becomes pi over 6, plus, we're going to put pi over 6 in for this theta. Pi over 6 times 6 is going to be pi. Sine of pi is 0, so that's gone. So we get a 0 there, minus, now we put the 0 in here, we get a 0. Here, of course, we get sine of 0, that's 0 as well, so that's going to be 0 as well. So again, that's our f of b minus our f of a. So all we're left with is 6 times pi over 6, or just pi. So the area of that 3-leafed or 3-petaled rose turns out to be pi. All right. So that's how you do the area problems. And you're going to want to always try to make use of this symmetry when you do your angles. That's why we draw our graph, take a look at the symmetry beforehand, and it makes the calculations a whole lot quicker and a whole lot easier. So that's how we do the area problems. What about one of the arc length questions, right? What about one of those? Back to the homework. So the arc length problems were 19. I'm looking at the wrong homework assignment, I apologize. They were 19, 21, and then we had to find 35 and 36. Okay. So I'll work on 19 and 21. Again, you're going to draw the picture and use symmetry again there, all right? We're going to want to use symmetry when we do our angle from A to B. If we had a similar picture, let's just hypothetically, before I do another problem, let's say we had a 3-sided rose like the problem we just had. All we have to find is the length of this arc right here, and then multiply that by 6 to get the length of the whole three-petaled rose. So we don't want to overlook the power of symmetry when we do these problems. So that's how you would do 19 and 21. They're very similar to the problems we've done, except you just stick the formula in the arc length formula instead of the area formula. So I'll take a look at problems 35 and 36. I'll do 35. So problem 35 gives us R equals 3 sine theta. And we have the angle is given to us as 0 is less than or equal to theta is less than or equal to pi over 3. And it says find the length of the exact length of the polar curve. Now our formula here is arc length is equal to the integral from A to B. And then we have our arc length formula. So we're going to have a square root. And remember, it's somebody squared plus somebody squared. That's typically the way the formula goes. Sometimes one of these two terms is a 1 if we're happening to be doing it with respect to y or respect to x, but it's still 1 squared, even though we don't write it that. But in polar, it's r squared plus dr d theta squared d theta. And we want to do this between theta equals 0 to pi over 3. So what does this look like? If we draw this, we're going to draw the graph of 3 sine theta. Just again, it's not imperative, it's not required that you draw it, but for me, it just makes more sense if I can see what I'm following the arc of. We're just drawing the graph of sine here, 3 sine. So this is going to be 3 and this is going to be -3. And we only want to go from 0 to pi over 3. So we know if this is regular sine, this is 2 pi, this is pi over 2 right here. So if we were to redraw this in polar form, right, our r is here. Remember, this is r and this is theta. So we're at 0, 0 right here. R is 0, theta 0. By the time we get to pi over 2, which is here, we have extended out to 3. So we have an arc that looks like this, where this is 3. But we don't want that, right? That whole piece. We only want the piece from 0 to pi over 3. So we're looking for the length of something that looks like this. Because as we go to pi over 3, which is here, our radius just keeps growing and growing and growing, right? And we're only going to pi over 3. So I guess I should draw that at pi over 3. So we're only going to here. So we want to know what's the length of that segment. Wow, I said pi over 3 and I wrote pi over 2. So to do that, we're going to have to plug it into our formula here and hope that something good works out for us. So what do we have? We're going to have the integral from 0 to pi over 3. We're going to have the square root of r squared. Now r squared is going to be 9 sine squared theta. Plus dr d theta squared. So we can come over here to our scratch area, do dr d theta. The derivative of 3 sine theta, of course, is going to be 3 cosine of theta. So when we square that, we're going to get plus 9, right? 9, 3 squared, cosine squared theta, d theta. And that's wonderful because we can factor out a 9, right? And when we take the 9 out of the radical, it's going to be a 3. And then under the radical, we're left with sine squared theta plus cosine squared theta, d theta. Well, sine squared theta plus cosine squared theta is 1. So this turns out to be the integral from 0 to pi over 3. We can put the constant out in front. We're just integrating d theta. So we have 3 theta evaluated from 0 to pi over 3. And when we multiply, we put the pi over 3 in here. So we're going to have 3 times pi over 3 minus, we put the 0 in here, we're going to have 0. And so we get pi again. That's the answer we got to the last problem. Okay, so that finishes the homework videos on H1 and H2. I'll see you in class, and I hope this helps you.